We ended off yesterday with this problem, 21, chapter 10, and we were taking a look at the solution for that, getting the moment of inertia about the x-axis here in chapter 10, number 21. So I set it up here that, I have moment of inertia about the x-axis is basically the axis that's spinning, or that everything is spinning with respect to, spinning about that axis. And so we calculate the different moments of inertia, which is going to be, say M1 R1 squared for whatever mass you pick first, M2 R2 squared, and so on. So our first mass about the x-axis chose as 3 kilograms, and it has a distance of 3 meters away from the axis itself, because this entire distance is 6. Let's see if I can just colorize it a little bit. That's 6, 4 down below. Yeah. So all we're just doing, find the axis of rotation, as we've been doing with all of our problems. In this case, find the axis of rotation and the distance away from the axis and the mass that's spinning about it. Calculate the moment of inertia. 3 kilograms times 3 squared plus 2 kilograms here times 3 squared, 4 times 3 squared, 2 times 3 squared, and we have the entire moment of inertia of the system about the x-axis. And so when we calculate all that, we're going to get roughly 99 kilogram meters squared. The units of moment of inertia are kilograms meters squared, because kilograms times meters squared. And then likewise along the y-axis, 3 times 2 squared, 2 times 2 squared, 4 times 2 squared, 2 times 2 squared, because those are all the distances away from this axis of rotation. Here is 2 meters all the way around. And when we calculate that, we're going to get 44 kilograms meter squared. That is a 4. Right, and then they have this propped up here. Then they want you to, the principal thing is to calculate about the z-axis. So we just add them together, and that's going to be roughly 143 kilogram meters squared. And then the rotational kinetic energy about the z-axis is going to be 1/2 times the moment of inertia here, times the given angular velocity, 6 radians per second squared. That's radians per second. All that squared, right? And that'll give us our rotational kinetic energy. Hopefully you guys got that already. Why is not my calculator available? Okay. So that's 2,574 joules. Of rotational kinetic energy. So our masses in this system rotating around some axis, X, or Y, or Z. If in V, it'd be looking like something like Okay. Oh boy. And the z-axis is something like this. I mean, it would be the original orientation this way. And it just starts spinning about in place. Anyway, that was a crude picture. But anyway, we'll take the whole thing and just spin it in the plane, clockwise or counterclockwise, it doesn't matter. And then I asked you guys to do question 22. Did you guys do that already? Why don't you take a few minutes if you haven't done it to do question 22? Or did everyone do that already? Let's take about 5 minutes to just do that one. Okay, so we have the system here. Y equals +3. Y equals -2 meters. Again, this is the are you doing these weird things? This is the axis of rotation, x-axis, y. This guy is 4 kilograms. 2 kilograms, 3. You know, it's spinning. So the top is coming out of the page, going back in. So, you know, it's a vertical rotation. And if it was rolling at the same time, we could find out what the linear kinetic energy would be if we found out what the velocity of the center of mass is using the center of mass equation. And then we could like combine everything, and then we start getting, you know, crazy with it. And, okay, it has rotational and linear kinetic energy. And if we put it on a height, we can find out the potential energy. And, you know, and we already have the moment of inertia. We can do all kinds of stuff. So, so part A, they want you to find the moment of inertia about the x-axis. So we have m1 r1 squared, m2 r2 squared. So this is a sum. That's why the sigma was there. You know, the main guy is mi ri squared. It's the sum. So let's take it over here. Sum those guys together. So 36, 8, 48, 44 plus 48. 92 kilogram meters squared about the x-axis. Hopefully everybody got that. Any questions? Next, we are to find the total rotational kinetic energy about the x-axis. So we're spinning about this axis here, 1/2 Ix omega squared. And 2 radians per second squared. So again, so that's to that. $184 joules. And the tangential speed of each particle and the total kinetic energy, linear kinetic energy of each one. So part B, I want you to find the tangential velocity of each mass. So all of them have different radius. So we'll just say VT of our first mass, which is 4 kilogram mass up top, has a distance of 3 meters, spins at 2 radians per second. Then we VT2, and the tangential velocity of our third mass, which is the 3 kilogram mass at the bottom. Well, I'll just be more specific here. This is the tangential velocity of the 4 kilogram mass, the 2 kilogram mass, and the 3 kilogram mass here, and their distances. So 3, 4 meters. It's going to be 6 meters per second. So the total kinetic energy is going to be the sum of all of these guys. One half on the outside, doesn't really matter. So 1/2 of all of these guys. So we'll take 4 kilograms. Multiply that by 1/2 distributed out. So $144 is 1632. 192. That's 184. Total joules of linear kinetic energy. And look at that, our rotational kinetic energy is the same. It says to then compare the answers for kinetic energy in parts A and B. Well, we can clearly see that they're the same, and we can make a further evaluation of why they're the same. Why do you think they are the same? Anyone's guess? You want to take a stab at that? Well, basically, they're all spinning with the same rotational angular velocity. So your rotational kinetic energy, which is the sum of all of those masses, is going to. So if you think about it, those are all point masses from a particular distance from the x-axis. You sum all those masses together, even those masses and any other mass, you're going to come up with a large mass, which is the sum of those smaller masses that is moving with one translational or tangential speed. So with this one tangential speed, you're going to have a particular kinetic energy. That linear kinetic energy is going to be the same as the rotational kinetic energy, because all of those masses are spinning about with the same angular speed from the middle. So this rotational kinetic energy here is going to be the same as linear, because all of those masses summed together are going to be moving at one as it rotates. So we're just kind of seeing it indirectly that that rotational kinetic energy and linear kinetic energy are the same. Did anybody get something different than these answers? Anybody have any questions? All right, so let's introduce unbalanced torques. I'll do a introduction on that, sample problem, and I'll give you a sample problem. Okay, and we'll be done with that part. So in your textbooks, we're going to go to section 10.7. Rigid object under a net torque. So far for the last 3 or 4 days, we've been looking at balanced torques, things that are static, not moving, and we've been evaluating certain things from that. So now we're going to take this system and get it moving. We're going to have our mass pulley system that's moving, with a linear acceleration as well as angular acceleration. So we're going to be doing the same things, similar things that we've done before with the balanced torques, where we have force equations and a torque equation. But now we're going to have force equations with an unbalanced torque equation. So first, let's look at what torque looks like when a system is moving with angular acceleration as opposed to, in addition to linear acceleration. So rigid object under a net torque. Okay, so far we have seen that torque is some net force that's perpendicular to some radius. We know that a net force is equal to MA linear net force, MAT, for tangential acceleration, MAT times R. And this is, for 1 point mass. It's moving around a circle under the influence of some net force. Saw that at the beginning of chapter 10. We can extend torque over a whole object. So instead of one mass, we have a collection of masses. The sum of all of those torques, sum of all the individual net forces, times radius. Sum of all their individual point masses with their individual tangential accelerations times R. So we have an object spinning and you have all these different point masses and you're just summing them all up. This one has an AT, all these ATs together to make a sum, to make a collection that forms a sphere or a cylinder or a ball of some kind or whatever shape it is. I'm just dealing with one mass with a collection of mass. Not one point mass, a distribution of mass, which we call moment of inertia, spinning about some axis, etc. Right? So that's, again, still remains our picture. Assuming MATR, and in terms of the angular quantities, the linear acceleration is going to be R times alpha, so we can just make a substitution. R alpha R, and then this becomes mr squared alpha. And we've seen yesterday that mr squared is the moment of inertia term. So therefore, the sum of the torques, or the torque net, is equal to moment of inertia times alpha, which is very similar to F net, or sigma F, mass times acceleration. So that's the rotational analog of the linear force. It's just a collection of terms. We rotate it, as opposed to dealing with just lines X or Y. Okay, so we're going to need that as we go through our example. Questions? So again, torque over a whole object, right? Net torque, yeah, you get it. All right, so the example, yeah, sure, just let me know. Okay. Yeah, continue in a minute. As part of that, make sure you understand how that works. And don't be shy on any questions, because you must visualize this. You can't just take the notes down. You have to see it. If you don't see it, please ask. So the example, I'm going to go and give you a problem. Okay, I'm going to get right to nitty-gritty, cut out the middleman. I want you to go to page 303, number 37. Let's dissect that for 10 minutes or so, and then have you do a sample problem. Similar to that. At least the logic will be similar. So we are page 303, 37. All right, I'll get my feet set. Okay. So we have the pulley here. Call this M2. M1. It's the same string, has the same tension in it. And let's read the problem. A block of mass M1 equals 2 kilograms. And a block of mass M2 equals 6 kilograms are connected by a massless string over a pulley. In the shape of a solid disk having radius r equals 0.250 and mass of 10 kilograms. These blocks are allowed to move on a fixed wedge of angle theta equals 30 degrees, as shown in the figure. The coefficient of kinetic friction is 0.36 for both blocks. We got a lot going on. Draw free body diagrams of both blocks and of the pulley. Determine A, the acceleration of the two blocks, and B, the tensions in the string on both sides of the pulley. So before, when we were doing force problems, we were ignoring the pulley, the mass of the pulley is negligible. Now that's going to be very important because we have a torque that's going to be, two different torques that are going to be exerted about this pulley. One string is going to pull it in one direction, the other string is going to pull it another. So we have to be careful as to the directions of those pulls so we understand if the torques, which torque is clockwise and counterclockwise, which one is going to be a positive torque and which one is going to be a negative torque. Yes, it's the same tension T, but the directions of the pulls are different. So we're going to have to designate these T's by, say, T1 and T2 because both of them on either side of the pulley are going to act differently. Okay. The force is the same, but the torques are different. Because this T down here will pull it one direction, this one up here, pull it the other, different torques. So we must designate them appropriately. Torque 1, torque 2, T1, T2. All right. So first thing, free body diagrams as they stipulated. So let's draw a free body diagram for the guy up top. Very easy, huh? Have normal force there. Negative mg. T1. Moving, kinetic friction. This should be smaller than T1, but you get it. You know, the acceleration is going to be that way. linear. Then the guy on the ramp, Fn and G. And of course, you know, typical G cosine theta, G sine theta. And so this is going to be negative T2, negative Fk. So again, I have the T1s and T2s in there, even though it's a force equation, because just to keep consistent, this is going to be a torque situation happening here. T2 is going to be providing a different torque than T1. So T2, its torque, T1, its torque. So now let's get the free body diagrams for the pulley. So step 2, right? So on the horizontal, T1 is going to pull, if you just look at T1, it's going to be pulling it, you just ignore everything else. T1 will be pulling it in a counterclockwise fashion. It's going to cause the pulley to rotate counterclockwise. So its torque will be positive. Well, you get it. Yep. Then T2, torque down the ramp, it will cause the pulley to go this way, clockwise. Perpendicular, perpendicular, everything consistent. You get that part. So we have to designate the T's. We have to separate them out because there's two different torques, two different directions of pull. That's the thing that changes. Step 3, get your force equations and the one torque equation. The key here is going to be that torque equation. Okay, in order to solve for stuff. Your free body diagrams, you know how to do that. T1 minus Fk equals M1A, familiar. Fy, and this is for the first mass, you know, you got that. Fx2, second mass. M2G sine theta minus T2 minus Fk equals M2A. This is going to be Fn minus M2G cosine theta equals 0. So we got everything for our free body diagrams, our force equations here. Again, the acceleration's down. So that's why, you know, this is going to be positive, these negative, you get that, positive, negative. We need them because there's a friction. Now, our torque equation. So we have two directions of pull. T1 is going to go counterclockwise, and T2 is going to go clockwise, both with the same radius. We just stipulated that net torque is equal to moment of inertia times angular acceleration. So these are the torques that make up I alpha. Now, since this is a pulley that's a solid disk, we have to substitute the expression for that particular moment of inertia. In this case, you have a solid disk. Next, you could have a cylinder. Next, you could have a sphere. You could have any type of different shape. So you have to put the particular moment of inertia in there, or substitute it at the end, but you can do it now. So now you're going to look in your textbook. The table moments of inertia. You can find those on page 278. And as you get to page 278, you'll see that the moment of inertia of a solid cylinder or disk is 1/2 mr squared. So we're not going to put I alpha here. I'll put it there for the moment. That's going to be the moment of inertia is 1/2 mr squared times alpha. Now here is the deal, the visual, the whole shebang, whatever. We know that the pulley is going to be rotating with an angular acceleration. The whole system, though, moves with a linear acceleration. So the pulley is in place, it's rotating, yes, cool. It has an angular acceleration and all that good stuff, you know, whatever, and this way or that. Alpha. The whole, but the deal is the whole system is moving as one with a linear acceleration. So we can translate this alpha into a linear, or in terms of its linear acceleration. And how do we do that? So let me just expand this out. T1r minus T2r 1/2 mr squared, and then the alpha. So you know that linear acceleration of the pulley, the points on the outside of the pulley have a linear acceleration. The inside, the whole thing rotates with an angular acceleration. So AT equals R alpha. So alpha is going to be equal to A divided by R. So we can make a substitution there and have everything in terms of A, because the whole system is moving with a linear acceleration. The angular acceleration is not important, only if, I guess, if the whole system was rotating and staying in place, but the whole thing is moving with the linear acceleration. Yes, it is. 1/2 for, yes, we got to keep that. 1/2 mr squared, so circle will be mr squared, a sphere will be 2/5 mr squared, some version of mr squared, because we derived yesterday the expression for moment of inertia, which is mr squared, and then all the different geometries, all the different shapes take a form of that. You can see on page 278. Hollow spheres are different than thin cylindrical shells and all that good stuff. So there's ways to calculate that. You have to use calculus to do that, but at least the most efficient way. Get that out of here, and then we have T1r, T2r equals 1/2 mr. We want to do alpha. MRA. Now, one last thing before we go to solve this. We have our torque equation. We know that the system is moving down the ramp. So the torque that is involved, or the part of the tension that's on that side of the pulley, is the tension that provides a clockwise torque. Okay, say that right. The system moves down the ramp. This part of the tension provides, this part of the tension that goes down the ramp, because the system moves down the ramp, that part of the tension provides a clockwise torque. So the net torque in this system is going to be negative. That means that this expression here will be negative. If it was going up the ramp, positive. So that's the final piece, and then we can just solve this guy out. Questions there? Not only do we have to get the free body equations for the torques and determine the directions of the torques, we have to get the direction of the net torque, because that's important. It's that shows what part of the tension dominates. Oh, it's the part of the tension that provides the clockwise torque. So the net torque is going to be negative. Just like if you had a pulling force that's greater than the force of friction going left, you're going to have a positive net force or a negative net force. It's the same idea. So now let us continue and just sum all of these. What I'm going to do next is I'm just going to put all these guys together, because this is a big sum. These are all the linear system of equation problems. Okay, so I'm just going to take everything at once from those force equations. I have T1, because that was the friction force, Fk. Cosine theta, not all equals to M1A plus M2A. So again, I just took all these and I, expanded this Fk, mu k, M1G, which is this, all that. Now I'm going to deal with the torque equation here. T1R minus T2R equals negative 1/2 MRA. Yeah. Yep. And these goes away, and so I have T1 minus T2 equals negative 1/2 MA. So you can see that, okay, I have my angle theta. I know what all these guys are, but T1 minus T2 is going to be sticky if I don't do something correct with my torque equation. And now I have an expression for T1 minus T2, which is negative 1/2 MA, put it in there, and I can solve for everything in terms of A. No alphas needed, all that other stuff. So, and the reason why we do that is because our whole system moves with a linear acceleration. The movement is still linear, but we have to deal with that pulley. Okay, so and everything just dominoes. Okay, so we put all the A's together. Okay, at this point, it's just algebra. I mean, okay, so assuming that you can do that. So I'm gonna put everything over here. So it's this stuff will be ditto. Everything, all this is the ditto stuff. And I'll put everything at equals. It's going to be A equals. And I'll just come down and put the expression for A. So we'll just cut out some writing here. When you put all your numbers in there, again, you can do this as an exercise. Prove that this is 0.31. So you do this, put the, just prove it to yourself. All right, we'll come back. Let's go and solve for T1, T2. Let's use the first equation, shall we? It's like we do back in the day, chapter 5. T1 M1A plus UK M1G, that was the FK, it was a minus, and that was plus. I'll always squeeze that there. That will be, do all that. It's going to be 7.7 newtons for T1 up top. And we can use our torque business. T2 is going to be equal to T1 plus 1/2 MA. It's going to be equal to 7.7 plus 1/2 of 10 0.31. That comes out to be 9.25 newtons. So T1, T2. Any questions there? So that's that huge example. Now, logically, I'm going to have a pulley for you to do 2 masses. The logic is the same. Free body diagrams, get the torques, put your force equations in, your torque equations, solve. Those are the steps. Let me just go back. I like to do method. Draw your free body diagrams. Get your free body diagrams for the torques. Put your force equations down and your torque equation. Be wary of where the system is moving to know if the net torque is positive or negative. Clockwise, counterclockwise, or clockwise. In our case, clockwise, so negative torque. Net. Chop it up. Okay, so now I would like you guys to just do question 44. for the rest of class. Okay, and we'll come back. 2.1 for the acceleration. Let's go set up 44. We come back next time, complete it, and go on. So let's see, we have so this guy is up. This is M2, M1. So the system's going to be moving that way. So one is larger. First thing we want to do is get our free body diagrams, all y direction for mass 1. So we got T1 because he goes against the system. Rage against the system. Okay, and then we got T2 here and negative M2G. So we have negative T1 plus M1G equals T2 M2G. Let me just add everything together. And we'll deal with the torques in a second, but just to set this up, okay. So in terms of the free body for the torques, and so we have T1 left on its own pull. No, there's no FN. It's off the floor once the system moves because we're not static. So we don't care about the FN even for a moment. The system's moving because 20 kilograms is on the left. That's just scenery. All right, so T1 pulls down, so it's going to cause a counterclockwise torque. And T2 is over here, left alone, is going to cause a clockwise torque. It's going to spin it that way. And, you know, a couple more minutes. So we have our T1R minus T2R equals I alpha. And it's a solid disk, so we have to put the term for the moment of inertia here, 1/2 mr squared alpha, and then alpha is going to be A over R and so on. So I'll leave it there. We will come back. But did anyone get 2.1 since the last time I asked? So we still need to see that. We will take care of it, and obviously have more examples in this to make sure that we have it. Okay, don't worry about it. We will. we will conclude, we will get something, we will get 2.1, we will get more than that, we'll do more examples. So don't fret. Okay, so that's it. I'll give you some examples on balanced torques or homework on balanced torques for next week. And we'll come back next Wednesday and do more of this. Take care. See you later. And then if anybody's coming after school, I'll be here at 2:35, office hour link.